High above Earth, more than 35,000 kilometers away, lies one of the most valuable regions in space, geostationary orbit, or GEO. Here, satellites maintain a fixed position relative to Earth, providing vital services like communication, weather monitoring, and broadcasting. Currently, there are approximately 540 operational satellites in GEO, and each one is a high-value investment. A single satellite can cost up to $200 million, with total deployment costs soaring as high as $400 million. But these critical assets are vulnerable. In October 2024, Intelsat 33E, part of Intelsat's advanced Epic NG series, suffered a power failure that cut its mission short, resulting in a complete loss. The failure wasn't just costly, it left behind a trail of debris, fragments that are now being tracked by the US Space Force and private organizations alike. And this is not an isolated case. Over the past 2 decades, solar panel failures and anomalies in power systems have plagued multiple GEO missions, from Superbird 6 in 2004 to Venusat 1 and Intelsat 19 in later years. These failures underscore a critical issue. GEO satellites are breaking down, and we're running out of sustainable ways to respond. Solar panels in space degrade up to 8 times faster than on Earth. Without intervention, a satellite's power supply weakens, limiting operations or causing total failure. Replacing a satellite is expensive and time-consuming. The more sustainable answer, servicing and repairing existing satellites before they become space junk. With more satellites failing, debris building, and costs climbing, the call for action has never been louder. At San Diego State University, a team of engineers is answering that call with a bold new initiative, a mission designed not just to fix what's broken, but to redefine what's possible in orbital operations. Introducing ORION, the Orbital Restoration through Innovative Operations Network. As the number of satellites and debris in space continues to rise, so do the stakes. ORION sets out to change the way we maintain and sustain our most valuable space assets. At the core of ORION is a 2-tiered system, a central depot satellite, and a fleet of 6 astellar servicer satellites. Each servicer is equipped to rendezvous with active satellites in GEO, perform solar panel repairs, and replace degraded power systems, all while operating autonomously or semi-autonomously. The depot serves as the operational hub. It stores spare solar cell arrays and carries enough fuel on board to enable servicers to conduct up to 3 full missions before needing to return to Earth. By replacing failing solar arrays, ORION restores power systems and extends satellite lifespans by 5 to 15 years, preventing costly replacements and minimizing orbital clutter. With each mission, ORION not only revives satellites, but it also helps avoid the creation of dangerous debris in orbit. But ORION doesn't stop at servicing. It's equipped with LiDAR, infrared cameras, and star trackers to detect and track debris, helping secure the GEO environment for future missions. The ORION mission is guided by a focused set of objectives. The first being to repair active satellites in GEO using multiple servicing vehicles. The second, to store faulty components from active satellites in GEO using a depot. And third, to demonstrate the capability to perform in-orbit refueling operations for satellites in GEO. In addition to the mission's primary goals, ORION's secondary objectives are to passively identify and track debris, and to demonstrate satellite relocation to a graveyard orbit. To prove the effectiveness of ORION, our team has identified a real-world client with a clear need and a promising opportunity for impact. Meet Intelsat, a leading global satellite operator with a fleet of high-value assets in geostationary orbit. Specifically, we've focused on their Galaxy series, which includes 2 clusters of satellites positioned at longitudes 85 to 99 degrees west and 121 to 133 degrees west. Each cluster contains satellites with similar inclinations, altitudes, and orbital characteristics, making them an ideal target for a multi-servicing demonstration. The geographical spread of these clusters also allows us to test long-range servicing operations within a confined region of GEO, minimizing fuel demands and reducing transfer complexity. These 15 satellites represent more than just Intelsat's infrastructure. They represent a testbed for future GEO sustainability. With a potential client identified and our mission objectives clearly defined, the next step is building a system capable of delivering on that promise. Every element of ORION, from the depot to each individual servicing satellite, is driven by a set of well-defined system requirements. These requirements ensure that our mission isn't just visionary, but it's achievable.
Guidance, navigation, and control is a critical aspect of this mission. The servicer satellites will need to semi-autonomously dock with our depot in order to refuel, and this can be a challenging task that requires precise control. We will also be passively tracking debris for collision avoidance purposes. Key components include what you see here: reaction wheels for precise attitude adjustments, RCS thrusters for translational control and desaturation of the reaction wheels, star trackers and gyroscopes to provide accurate orientation data, and star trackers also help our debris tracking. GPS receivers provide reliable position and velocity accuracy. Sun sensors help us align towards solar arrays for power generation. All these systems work together during critical mission phases, such as rendezvous, approach, and docking to ensure precise alignment and reliable performance. The top graph here shows a simulation of the approach of the servicer towards the client satellite with an initial position and velocity error. This graph was modeled in hill frame, meaning that the motion is relative to the client, with the client being centered at the origin. This is a common strategy used in close proximity operations. To make the correction, we use a continuous thrust via APD controller. The thrust over time graph is shown on the bottom, governed by the thrust equation shown. In this graph, it can be seen that there is a high thrust at the beginning to correct the initial error. Then there is a smooth drop-off as the trajectory converges. Finally, it shows the controller throttling as the servicer approaches the client. To simulate this approach, the Hill-Clausius-Wiltshire equations are used. This is a simplified set of equations that can be used to model the relative motion of two spacecrafts in space. It is sufficient to use for close proximity rendezvous scenarios such as the one we are simulating. This also assumes circular geo-orbit. This graph is the delta V accumulation over time. This shows the total integrated acceleration applied by the thrust. The total delta V used is 0.256 meters per second. This next graph is the relative velocity magnitude over time. It starts high due to initial error, then decreases steadily to match the client's velocity, and almost reaches 0 meters per second.
The servicer's most critical phase is during the close proximity operations, as it approaches the depot for fueling and client satellites for servicing. As we know, the BCT XSAT Venus class bus already includes various components. However, additional instruments are needed to ensure requirements are fulfilled. The LiDAR rendezvous docking sensors fulfills the first requirement, and the astrohead camera fulfills the second requirement. These operations will be autonomous. However, if risks arise, we're able to connect from ground to manually operate. The requirements for the attitude determination are as follows. The depot must be able to plan its path from cluster 1 to cluster 2, and the servicer must be able to plan its path from the depot to the client satellite and vice versa. The servicer must also be able to actively sense its own position and orientation and make necessary attitude adjustments. Methodology is as follows. Each servicer has a designated path as it travels between the depot and the client satellites. Since our satellite system is in GEO, the depot and client satellites' orientation always move at the same speed as Earth, which is useful in determining the servicer's orientation readjustments. As the servicer travels to each client satellite, it changes its orientation depicted in the plot to the right by Euler angles. In this particular case, the plot depicts servicer 1 as it leaves from the depot to client 1 and client 2 at 97 and 92 degrees respectively.
The payload subsystem of the depot is responsible for enabling servicer satellites to replace solar cells of client satellites, as well as track space debris in GEO. This includes carrying enough consumables for 9 resupply operations in the forms of solar cells and fuel, as well as special sensors used to track the space debris in GEO. Here's an animation of the docking process of the servicer to the depot. As you can see, the servicer starts at a faraway orbit before transitioning to its final orbit. Once final orbit is achieved, the servicer is then rotated until its docking face lines up with its corresponding docking port on the depot.
A portrait plot is needed to determine launch windows for the mission. By determining the departure and arrival dates with delta V values, the ideal launch window will be shown on a plot. For this particular mission, some limitations are set. The atmosphere threshold of 100 kilometers to avoid computer transfers to have a possibility of colliding into Earth, as well as 200 kilometers above Earth as the point of insertion into geostationary transfer orbit after launch. The left image shows the transfer path of the geostationary transfer orbit to geostationary orbit. Under these circumstances, along with astronomical properties of Earth and geostationary orbits, the time of flight it takes for a Hohmann transfer is calculated to be 5.2588 hours, with a delta V value of 3.932 kilometers per second, shown as the black line in the plot on the right. The dotted red lines are different values for the time of flight of 5, 6, and 7 hours. All 3 sets of time of flights show that within these given regions of time of flight, the delta V values are still achievable, allowing little room for errors of the launch.
To meet the mission servicing goals, the depot must fulfill several trajectory requirements. First, it will require precise insertion into geostationary orbit. Then, It must perform an inclination change maneuver as well as phasing maneuvers to align the depot's orbital plane and its longitude with the servicing targets. At the end of the service life, the depot must also execute a relocation to a graveyard orbit. Throughout its 10-year lifespan, the depot must also support multiple rendezvous with astellar servicers. All of this must be accomplished with a delta V budget of around 3 kilometers per second. We analyzed two mission alternatives. Case 1 with the depot starting from LEO and performing sequential burns to reach GEO, versus Case 2 with the depot beginning in GEO and using smaller maneuvers to fine-tune its position. We analyzed two mission alternatives. Case 1 with the depot starting from LEO and performing sequential burns to reach GEO, versus Case 2 with the depot beginning in GEO and using smaller maneuvers to fine-tune its position. This animation shows the home and transfer used for GEO insertion, with the launch vehicle executing the initial delta V to exit Earth's surface, and the delta V2 executed by the depot to circularize. This delta V2 is calculated to be around 1500 meters per second. After insertion, the depot will execute an inclination change of 2 degrees, with a calculated delta V of close to 107 meters per second. This step is crucial to ensuring the coplanar operations within the Intelsat clusters. Following the first set of operations, the depot would then execute a 2-burn phasing maneuver to adjust its longitude and align itself with the next servicing cluster. The initial delta V was calculated to be close to 409 meters per second, and the second one close to 346 meters per second. This data from the Eutelsat 28A showed frequent out-of-plane and in-plane station-keeping maneuvers to maintain orbital stability. Now, using this data, we derived an annual east-to-west station-keeping cost of around 46 meters per second, which we included in our lifetime delta V budget. Because north-to-south station-keeping is relatively low in GEO, it was neglected when considering the total delta V usage for the 10-year mission lifespan, which totaled out to about 2.93 kilometers per second, well under our mission requirements.
As the depot orbits around the Earth, it will experience a very dynamic thermal environment. It is crucial that the depot maintains a temperature between 293 and 303 Kelvin. Apart from our ideal temperature range, we also have to make sure that our temperature gradient does not exceed 30 Kelvin. An additional environmental condition is that in geostationary orbit, eclipses can last up to 72 minutes. The thermal loads we can expect in geostationary environment is solar radiation, albedo, and Earth's emitted infrared. With our thermal loading in mind, along with some quick estimates, we have selected ChemGlaze A276 white paint as our passive thermal control. Similar to our structural analysis, we will use SolidWorks built-in FEA software to do thermal analysis, both steady state and transient. Through our steady state analysis, we could see that the average temperature across the depot is roughly 300 Kelvin, and that the temperature gradient is also in that 30 Kelvin range. Through our transient analysis, assuming our worst case scenario of 72-minute long eclipse, we can see that the temperature across the depot only drops 8 Kelvin, satisfying our subsystem requirements.
For communications, we have two main requirements. The data rate needs to support real-time operations with a high of 21 megabytes per second, and the bidirectional relay of information between service satellites, the servicer, the depot, and ground stations. This is in support of the transmission of health data from Intelsat satellites, verifying the servicer is carrying the necessary tools, solar panels, and sufficient fuel, proper docking support through real-time video transmissions, and passive debris tracking which operates 24/7. On the right is a high-level overview of our communication links. The servicer operates an X-band for uplink and downlink to ground stations. The depot operates an X-band for downlink and S-band for uplink, and intercommunication between the servicers and depot operates an S-band. A high-gain phased array antenna will be mounted at the bottom of the depot continuously pointed towards Earth. Several low-gain patch antennas will be strategically placed around the depot. As I just mentioned, we will be operating an S and X band. We chose S-band for TT&C, which offers reliability for lower data rates, and X-band for high-rate transmissions, which are necessary for debris tracking and real-time data exchange. Our servicers are operating in phasing orbits, which means multiple ground stations are necessary for global coverage and redundancy. However, the depot will consistently be over Hawaii and Florida. The table on the right summarizes the 5 ground stations we will be utilizing, of which operate in KSAT and SSC. On the lower left-hand corner are 2 antenna capabilities in particular provided by Blue Canyon Technologies that we agreed fit the requirements of our mission. They will both be mounted on our servicers and depot for added redundancy and latency purposes. On the left is a summary of our communication components, which totals our mass, size, power, and cost. On the right is a summary of the data rate requirements for each subsection.
At the high end, our data rate for real-time operations totals 21 megabytes per second, and debris tracking will be sent to grounds and batch data every 5 days.
During its lifetime, the depot must provide adequate power to all subsystems, most notably during eclipses. Using body-mounted gallium arsenide solar panels, we can measure the normal vector of each panel as the depot rotates about its vertical axis to quantify how much power they produce. Through our analysis, we see that the selected power system will always provide at least 600 watts, and each battery will only discharge 17.4% of its capacity during an eclipse.
Communication. The depot is positioned in a geostationary orbit, remaining fixed relative to Earth's surface. It is equipped with a high-gain phased array antenna for constant Earth communication, as well as 3 low-gain side antennas to maintain links with the servicer and provide redundancy in event of failure. The satellite's position was computed using basic orbital geometry, and Earth's rotation was accounted for using a time-varying transformation matrix. Ground stations were modeled in Earth-centered Earth-fixed coordinates using the following equations to the left based on the ground station's latitude and longitude. The link availability was determined using the elevation angle between the satellite and the ground station. The equations on the left demonstrate how the link budget was calculated by substituting the obtained distances, transmitter and receiver parameters, and incorporating loss factors that were either calculated or sourced from the reference graphs in the textbook. This slide shows the depot's communication links for Cluster 1 and Cluster 2 using South Point, Hawaii and Clewiston, Florida as the primary ground stations. This next slide presents the servicer to ground link during its orbital transfer to Client 1, Galaxy 33. I have provided the ground stations in the animation, noting that only Japan and Hawaii are visible. The servicer specs are listed on the table, and the link budget graph and distance over time are also shown. Finally, we present the inter-satellite communication between servicer and depot during the docking phase. The graphs depict the link budget and distance over time, along with the elevation angle from the depot to the servicer.